up for Ron Minnich.
So I got a little jealous of Trammell's picture of Vincent, so I was trying to do this recursion thing, and it didn't quite work, as you can see with the banding. Yeah, so anyway, RAM payloads. So they always tell you if you do a talk, you need to have an outline. So I did an outline there. So, and then I thought that's not very, very informative, so, you know, I did a slightly more of an outline. So I'm going to talk about what a RAM payload is and why you would do it and how it is done. So I am not trying to claim here that this is something you would do on every platform. Mainly I'm trying to say it's something that might be useful on some platforms. So what's a RAM payload? I mean, it's kind of simple. It's just a payload loaded from the ROM stage. Instead of loading a RAM stage, you just load the payload from the ROM stage. And then that begs the question, because, well, what is a RAM stage? And a bunch of you in here know more about what it is than I do, but I'm just going to do my simple definition. The function of the RAM stage is to discover, allocate, configure, and enable resources roughly before booting. I left one thing out, have some means of communicating the information to the payload. It can, and this is more recent, right? So the first 8 years, this wasn't a thing. But since 2007 or so, it's been a thing, which is implement runtime firmware, SMM or S3. Linux BIOS, which this began as, originally didn't do that because it ran on supercomputers, and it ran on supercomputers in places that we absolutely did not ever want to have SMM running. I think even as early as 2000, we kind of knew SMM was a very bad thing. To put it lightly. The RAM stage is small on some systems and large on others. And so then, you know, some people say to me sometimes, well, wait a minute, Linux does that, right? Linux does all that discover blah, blah, blah stuff, so why aren't you doing it with Linux? And that kind of gets back to the beginning, and we actually never planned on a RAM stage in the beginning. In the beginning, actually, Linux was the thing we loaded. So here's the original ROM stage for Linux BIOS. Which was actually completely wrong, because between the time I stopped working with PCI card design and I got back into PCs again, this thing called SDRAM happened, which you know, I had not a clue about. So for what it's worth, when I started this project, I didn't have the faintest idea what I was doing, and it somehow worked out. So anyways, that's the first totally ridiculous ROM stage that didn't work. But, you know, okay, fine, that's the ROM stage. Let's pretend we got SDRAM working. Why didn't we do Linux as the RAM stage in the first place? Well, it actually turns out we did. In 1999, I did it with Linux 2.2. Didn't work. Get into that in a second. Interesting thing, I quick looked at all the binaries of the FSPs on GitHub, and they averaged to 450K, roughly, which is bigger than the Linux kernel that we were putting in Flash back then. Kind of a surprise. So here's the problem. I kind of stumbled my way through the SDRAM init and finally got that working, and stumbled my way through a bunch of early Linux startup. And now I plugged in an IDE device, and I got this far, and then it said, device disabled BIOS. And I thought, well, that can't be right. I am the BIOS. What did I do that I didn't know about? Did I kick myself in the back or something? And the answer was, no, we didn't do something behind our back. We failed to do something. And Linux back then interpreted not enabled as disabled in critical places. So, and here's the critical place in 2.2. IPCI.c, there's this loop across the base address registers, and if any one of them was 0, it would just say, oh dear me, the BIOS has just disabled the IDE PCI device, which of course we hadn't done, but we hadn't enabled it, and then it all just, you know, it went south at that point. So Linux 2.2 couldn't do it in 2000, and so we were really staring two options in the face. One option was fix Linux, right? Fix Linux is PCI and probing and all that stuff to work correctly when there wasn't a BIOS. I kind of pinged some friends of mine in the Linux community, and they kind of came back with, oh, you're just weird, so there's no need to fix this because it works for us. You're the only person, and it was literally true. I was the only person in the world with that problem, but you know, nevertheless, I was having it. And in 1998, I tried to get the 9P subsystem into Linux, and that took 8 years, and I didn't know that in 1999. But they weren't quite as open as they are today. And remember, this is pre-Git, pre-Bitkeeper, right? This is kind of like, I think they were still shuffling tar files around. I'm not sure. So the second option was fix Linux BIOS, and I went with Plan B. I grabbed the Linux PCI enumeration code and jammed it into Linux, and things kind of worked. And that became the ROM stage. And the thing we know as the device model came in kind of in V2. So, well, the work on Linux BIOS started in the second millennium, and now it's the third millennium. So now we've been around for like a millennium. It seems like a good time to think this through a little. And you know, the RAM stage has grown over time from this simple PCI configurator to a lot more stuff, but Linux has similarly grown in capability, and it can do a lot more of what the RAM stage does. So the question is, you can think of an intersection point in capabilities between what Linux knows how to do, what the RAM stage does. And the question is, you know, do we need the RAM stage? Is the intersection of capabilities at a point where Linux could just do what the RAM stage does today? And part of what drove this is the early RISC-V ports, there was no RAM stage. I mean, the only thing the RAM stage did in the early RISC-V ports is load the payload. And I get a little worried sometimes because I see the RISC-V RAM stage, and I got to talk to Jonathan and Philip about this, but I see things growing in a RISC-V RAM stage almost because they're looking at the x86 as a model, and that's not really a convincing reason to do that, right? So I kind of worry a little bit about what I see happening because I saw this happen in a RISC-V community. Well, if the x86 does this, we should do that. So the x86 has SMM, well, we'd better extend the privilege mode so we can make sure we can do a thing like SMM. So, you know, sort of jumping into the mud pond there, which is not always something you want to do. And further, in a lot of cases, we don't want the things the RAM stage can do for us. We don't want SMM, we don't want S3 resume, and we don't want runtime services at all. On a lot of systems, we don't need the RAM stage to enumerate resources. They're simple and hard-coded, or they're PCI, and we know how to enumerate PCI. And you know, SMP setup, actually in the earliest days of Linux BIOS, we did in a kernel. We did no SMP setup in Linux BIOS until about, I don't know, 2001 or 2, when we had to deal with the K7, which had a very odd style of SMP setup. And we have other ways to provision things like APIs. So, you know, if you look at the RAM stage, a lot of the RAM stage is kind of there in some places, arguably, to support other parts of the RAM stage. So that's kind of the reason for looking at this. So can we go right to the payload? I did this experiment at the coreboot conference in Denver in 2015 and kind of convinced myself that, well, Linux and Harvey actually could be loaded directly from the ROM stage. The code wasn't great, but it did the job and convinced me. And this is actually what we're hoping to do in UEFI. So here's UEFI today. That's a lot of binary blobs, right? And there's scary stuff. Like there's this stuff, right? This happens when Linux is running. What does it do? The OS Present app, what does that do? I don't know. And there's just a lot of stuff in there that's red, right, for me, blood red. And this is what we're working to. We're not there. But if we look at the SCC and PEI footprint in ROM, it's about 10%. And what we want to do is go right from that last step, which is the board init, right into Linux and Flash. And you saw uroot this morning. We want to have an initramfs containing uroot with a netboot or local boot. And if we desperately need to run some UEFI driver, we're going to run that out of Linux. So the big, big red mess in the middle is gone completely. And further, we're putting in this concept of this air gap, okay? And the idea is, like we used to do in Linux BIOS, that thing loads that thing, and this thing never talks back. And the reason is simple, we don't trust firmware. So that's a reasonable thing to not trust, right? Based on the last 2 years. So the runtime is gone, the OS Present app is gone, and this thing just runs. And that's what we're trying to work to. So it's a simple rule. If you don't own the firmware, then you'll be owned by the firmware. And we'd rather not be owned. So, by the way, little digression, the Linux boot community is pretty big, as Ryan showed. We've had a lot of discussions about signing. Now, we're getting right close to the edge of my lack of understanding of some of these things, but basically, as I understand it, the current model is that vendor keys get fused in to these fuses, and then you can lock out any further attempts to change them. That's just got to stop. So that's got to get fixed. The current model is just not acceptable, and here's a simple reason, one simple reason. Let's just say the ODM sets the fuses, and then here's a customer. I'll pick on Facebook. Facebook is a customer. If they want to do anything and get it signed, they have to go back to the ODM. Okay, fine. Now Facebook sells nodes to John Marie's company for him to resell. He's got to kind of go back around Facebook to this company. Then this company buys them from Jean Marie. They've got to go back to that company if they ever change the firmware. It's just not an acceptable situation. This is one of those cases where I think Chrome really completely got it right. You get a Chromebook, you want to change the keys, you change the keys, right? Because you are the owner. So I'm not even arguing here for open up all the source, give us all the source, GPL your source. I'm really just arguing for give us control of the machine we paid money for. That's a simple argument. So if anybody's interested in having this discussion Friday or Saturday, maybe we can sit down and talk about it, but this has really got to change. Another thing that we keep getting into for the last 18 months on this project, we've got to get from a point where we're doing docs by reverse engineering to docs. And you may hear that theme a few more times in the next day. Anyway, that air gap I mentioned is essential because it breaks this connection between you and the firmware that you don't trust. Now, it's not that people are bad or people are dumb. It's that people make mistakes. We all make mistakes, right? I make lots of mistakes. And if you have a model where someone is going to create a blob and that blob will be bug-free forever, and they're going to put it in this thing and they're going to sign it, and you are stuck with that blob, it's not a workable model, right? And if that is the model, and that is the model today, then your best decision you can make is simply not to trust that once you're booted. And that was the model from Linux BIOS, right? We locked out SMM. We heard a lot of stuff about it was impossible to create a server platform that didn't have SMM. Linux Network shipped well over 100,000 nodes with no SMM. They worked fine. So, in 2000, the plan was no SMM and actually no ACP because we knew a guy from AMD who had resigned from the ACPI committee because he told us it was just the exploit heaven and he didn't want anything to do with it. We're not sure what to do about ACP, but oh well. We did keep the air gap for the first 8 years of Linux BIOS until laptops, and I think we all know the story there. If you're going to do a laptop, you're going to do power management, and the only model you've got there is SMM and ACP. But what is a BIOS? And I got to thinking about this, and part of the reason is almost embarrassing. I wrote my first firmware 40 years ago this year, and it gives you some perspective. So in 75, Gary Kilwell, he's kind of the guy who invented the term BIOS for CPM. You loaded CPM from a floppy, and then in your 1 kilobyte EEPROM on your IMSI or Altair, right, you had this little library. And the idea is CPM set the rules, right? CPM said, if you're going to run me, you're going to implement this to our specification. So CPM ruled the roost, right? They defined what that interface was. Then comes 1980, and it got a little weird because IBM released the PC and they actually released the source code to the BIOS, but it was copyrighted. But this weird thing happened that it flipped, right? It's like the boat flipped over. All of a sudden, the thing that set the rules was the BIOS, not some kernel. And that's the initial condition to where we are today, where BIOS has set rules and we have to conform to those rules. It wasn't that way in the first couple of years. So where we are today is the firmware is 8192 times larger. It's a hardware adaptation layer. It's a vendor lock-in tool. I mean, you can pick your choice of these. I tend to pick them all. It's a complex operating system. It's a large collection of built-in vulnerabilities and exploits. It's a very inefficient way to access your services. And in my opinion, it's something you never want to use once you're booted. That's the reason for what we're doing here. And yet it keeps recurring. So the RISC-V model is we've got the super and user modes, and then there's this thing called machine mode, and machine mode is provided by the firmware vendor, okay? And do we have to do that? Actually, we don't. In the RISC-V, the one privilege mode, the kernel could load M mode, but we're all kind of working toward this model, and you can see the patches coming into coreboot where the firmware is going to provide the M mode, and it's going to lock out the kernel from changing it. That's called security in some planet or universe. But it really doesn't have to be that way. It's just the way we think about it, because that's how we think about everything, right? Firmware is permanent. It has a higher privilege than anything. It's the root of trust. And the only problem with all that is it's wrong because we can't trust it. So we have an untrustable root of trust. Now, I'm talking to one RISC-V company that's working with someone I know in DOE. They're not going to do that. In their RISC-V implementation, the M-mode code will be supplied by the kernel, not the firmware. So what's wrong with M-mode firmware libraries? Well, why would you trust it, right? It's going to be written by the same people, at these vendors off somewhere. I'm not pointing fingers at even the chipset guys. Somebody is going to hack this thing up because they're trying to get a board out in schedule, and they're going to insert bugs. That's what keeps happening. So why on earth would you want to trust M-mode stuff supplied by the kernel? The firmware. I can't think of a reason. And how and when do you update? If you have a bug in M-mode, you've got to reflash the firmware on all your machines. If you supply the M-mode with the kernel, you reboot, and you have the fixed M-mode code. So, if you have an M-mode security fix and the kernel supplies the code, you reboot, done. You've updated your M-mode code, you didn't have to reflash. Performance. What's the ABI for these things? It's always maximally paranoid, okay? If you write firmware that's going to be called by something, you'd better assume the thing calling you is bug-ridden. You can't trust it at all, okay? So you've got to do this maximal saving of state to make sure that you don't get hurt. I've been here before. On the IBM Blue Gene, one of the last series, in order to sort of preserve this IP layer, they created this giant blob of firmware. If you wanted to send a packet on the IBM Blue Gene Taurus, the idea was, let's call this thing in firmware to send the packet for us, okay? Well, when you called that firmware on Blue Gene, you had to do a full TLB and cache flush and change the page table route. So it was incredibly, horrendously inefficient. And all the guys who did kernels on Blue Gene, including me, we just ignored the firmware and we wrote our own code to send packets on the Taurus because we couldn't take that performance hit. So I'm just not a big fan of firmware I call because it hasn't proved to really be a great idea. And whereas on RISC-V, if the kernel owns the M mode, it can optimize calls to the M mode code. So here's the slightly, I think this is the thing I expect to get beat up about. Kernels should supply firmware services they need. And this is kind of building on last year where I was showing that a Linux kernel could supply the SMM code and use it instead of the firmware supplied code. If there's a firmware service mode in the CPU, then let the kernel supply the code it runs. That's real easy to do on RISC-V. Most of that stuff's defined in the coreboot Arch directories. Very easy to add that to Linux and have Linux set it up. And this policy, though, tends to act against this tendency people have, like M-mode code or whatever code you want to call it. People say, oh, we need this extra thing. I know, we'll just add another function to M-mode, then it grows without bound. That's what we've seen happen. That's why, BIOSes on PCs are now 8 megabytes of runtime stuff. So I also think it would force a degree of restraint in what gets put into M-mode. And it would also, this one's important, this stuff is always a lock-in. It's always a chance to lock you into a given vendor because they supply some firmware library and the equivalent of M-mode that no one else supplies, and now you've discovered you're dependent on it and you can't change vendors. Anyway, back to the RAM payload. That's my rant. There's a RAM payload fork on coreboot.org. The ROM stage loads the RAM payload. If that fails, it goes directly to the RAM stage. That's very handy for when things go wrong. I think we need to, I keep running across calls to run RAM stage that are followed by a die, but RAM stage never returns, or it didn't used to, because it's got a die in it if it fails. So we've got some kind of weirdness in the way we call RAM stage. A lot of it's historical and goes back, I know some of that code is 10, 15 years old. Anyway, if the RAM payload works, you get a prompt. Ryan talked about Linux kernel and uroot this morning. That's what the test I'm doing does, which I'm going to show you in a minute. So it changes 13 files. I added a new payload called Linux check, which made my life way, way easier. Linux check is intended to be a regression test that may grow over time, and all Linux check does is just hunts around the machine looking for things that might cause trouble for Linux. So it's a nice small piece of code. It makes sure you have a console, that the serial is set up, that the number of memrages in the 820 table is greater than 0. That's always nice. Linux will panic invisibly if that is 0. So, Linux gets handy for finding things that Linux will not tell you have happened. And the only problem I've found so far, once I got through some of this, is that coreboot ROM stage printing, at least for me, doesn't actually work in QEMU anymore. Don't know why yet. I added a RAM payload config variable in CBF as in run. I've called a call to run ramprog. This is kind of boring stuff, but I'm just going to quick run through it. In the UART8250IO, if config RAM payload is set, then I call UART fill LB, which adds a table entry for the serial port. And then in the, I created this function run ramprog, and that changes program loading.h. One weird thing, I added my own compact boot mem write memory table because calling the standard one that runs on the RAM stage brings in a lot of dependencies on tables that we don't actually create in the ROM stage. So it proved to be a lot simpler just to have a real truncated write memory table. In the source lib coreboot table, I just disable a few things. I enable CBM list, and here's the one that's been a little controversial since I started doing this. I've got a self-loader for the ROM stage, and it actually looks a lot like the Linux BIOS v3 self-loader. It's a lot simpler than the RAM stage version because I don't have anything in RAM more or less, right? So I just call it and move it all to memory. The pushback I got is we should only have one self-loader. My pushback on the pushback is self is a data structure format. Self-loaders walk that data structure format and take certain actions. Similar to ELF, I don't see a problem with having two self-loaders, one being very complex and one being very simple. So we can argue about that in the next few days when we're here. I'm sure we will. But that's my take on self-loaders. So that's it so far. What about ACP? Yeah, what about ACP? We're not sure about ACP. Trammell's work on heads, he actually was talking about loading ACP from a file in the initramfs rather than using one in the firmware because guess what? We don't trust firmware. So we're not quite sure what we want to do about ACP. It's just there have been issues in these ACP tables over the years. And so I don't think we'll want to quite do the full air gap with coreboot, but never know. So the summary is RAM payloads were the original Linux BIOS design. The RAM stage was created to cover for these Linux limitations. And they just haven't proven to be needed in all cases. And this began when I was looking at the RISC-V, and it continued when I was then looking at UEFI, when we were throwing away everything after the PEI. And it seemed worth going back and taking a look at what we do in coreboot. We don't want to use runtime firmware services because we keep getting burned by them, and that then makes the payloads look more sensible than ever. And we're looking at developing them for UEFI. That's, of course, just about work in progress. Coreboot, going to demo it, and U-boot on those processor architectures. And I've forgotten I left off power because this works on power. All right, so let me do the demo. So this is QEMU, normal.rom, standard RAM stage with a Linux payload. And as I mentioned, this is basically this is the kernel that Ryan was talking about this morning, along with uroot as the initramfs. So away we go. Okay, now we're up. That prompt is the uroot shell prompt. So, this varies, and I haven't done enough runs because I'm not a statistician, but it kind of is like an above 5 type territory most of the time. You can hammer me on my lack of statistical rigor, that's fine. And here's the RAM payload. Even in QEMU, you can see, same time, so I lied. Anyway, generally this seems to be faster, and it's not surprising because no way about it. If you load the kernel from the ROM stage, that's hard to see it being much slower than loading the RAM stage from the ROM stage and then loading the kernel from the RAM stage. So it actually works though, and apropos the PCI thing, we have a command in uroot called PCI, just prints the PCI bus, and we can do stuff like, well, show me your config space. And the thing I notice here is, if for those of you who really know PCI well, if you look at sort of config space 4, I don't think I've actually correctly configured that command register, but and I don't think, well, I think that might be a bar there, I'm not sure. So I'm not entirely convinced that the PCI configuration is correct yet, but I think it's fairly easy to deal with that kind of issue. Yeah, so that's kind of it. Work in progress. I think we can make this go, and I think we can sort of dispense with what the ramp stage does, and more importantly, we're trying, I'd kind of actually like this to be sort of competitive. You're going to be surprised to hear me say this, with UEFI boot, and one way to get there is not run the ramp stage. And boy, I'm also finishing really early, so you're going to, 5 minutes left? Oh, I'm not finishing early, it's time for questions.
Yeah, thank you very much. Yeah, have a round of applause. Thank you. So it's question and answer time. So you will be supplying the questions, Bill will be supplying the answers. Also, I've heard.
What's this? Who supplies questions?
Such a new thing for me here. Oh, it's so bright. So what do you need from other users who are interested in coreboot Linux RAM stage? Do you need tests already?
Yes.
Do you think it would work on real boards, or would you be interested in tests? Or
the reason I'm glad I'm here is because of the 2-day hackathon. I'm hoping someone comes up to me and says, I brought an x86 with coreboot, let's give it a shot.
Okay.
And further, yes, anyone who wants to jump in and give me a hand, the more we learn, the better, right? Maybe this will never work. I'm actually pretty sure on RISC-V it will work very well, depending. x86, not sure yet. We'll see. But yeah, anything anyone wants to do, I'd love to have the help, including code reviews, of course. So.
Any more questions?
All right.
Okay.
Thanks
awesome.
for coming.
Thank you. Have another round of applause for Ron.